It all began with one man, Albert Einstein. He predicted that any object with mass would warp the fabric of space and time, and if that distortion were strong enough, nearby objects would be drawn into the curved space. This is the phenomenon we call gravity. But Einstein didn't stop there. He believed that these distortions in space-time could travel across the universe as waves that compress and stretch space-time. Gravitational waves, rippling through the fabric of the universe, like the ripples that spread when we toss a stone into a pond. Scientists figured it would take a massive impact to generate such waves, and they realized that if two massive celestial bodies were locked together by gravity, they would spiral inward, speeding up until they finally collided. During that spiraling crash, space-time itself would violently ripple, sending gravitational waves racing across the cosmos. But how could we possibly know that? Even if gravitational waves did exist, they would weaken as they traveled across space. After all, gravity is the weakest of all the fundamental forces. Gravity is more than 10 to the power of 38 times weaker than the strong nuclear force. Even Einstein believed detecting it would be impossible. Invisible and untouchable, this ghost-like entity remained the subject of skepticism and debate for decades. But scientists didn't give up, because every equation, every line of reasoning pointed to its existence. In 1984, American physicists Rainer Weiss and Kip Thorne proposed that gravitational waves could be detected using a device called a laser interferometer. The problem was the astronomical cost and the very low chance of success. It was a high-stakes gamble, with billions of dollars on the line. But if it worked, it would go down as one of the greatest discoveries in history. After much deliberation, the National Science Foundation approved the massive detection initiative known as the LIGO project. LIGO is conceptually simple at its core. It sends laser beams down two long vacuum tunnels, placed at right angles and equal in length. At the end of each tunnel is a mirror, and the lasers bounce off these mirrors and return. The returning beams meet back at the origin and cancel each other out completely. As a result, no signal is detected. Everything remains perfectly silent. But if a gravitational wave passes through during this process, it slightly distorts the distances that the lasers travel. And when the beams no longer cancel out exactly, that's the moment a gravitational wave is detected. It all sounds simple, but the precision required goes far beyond our imagination. Gravitational waves distort space-time by just 1 part in 10 to the 21st power. That's like measuring the distance to Alpha Centauri, over 4.3 light-years away, and detecting a change the width of a single human hair. And on top of that, countless sources of noise interfere with the measurement. So the scientists built 2 identical facilities in separate locations, Hanford, Washington, and Livingston, Louisiana. To confirm a gravitational wave, both LIGO observatories must register the same signal at the same time. LIGO operated for 8 years, from 2002 to 2010, without detecting a single wave. Even in the face of failure, they poured 5 more years and massive funding into improving the system's sensitivity and precision. The upgraded LIGO began observations with nearly 4 times the sensitivity of the original, and in 2015, LIGO finally succeeded. It detected gravitational waves for the first time in history. They came from a cataclysmic collision between 2 black holes in a distant galaxy over 1.3 billion years ago. The wave lasted just 0.2 seconds. Compared to the 100 years it took to detect it, that moment feels absurdly short, almost meaningless. But within that 0.2 seconds, so much was contained. Until now, we've observed the universe through light, which means the universe we can see begins about 380,000 years after the Big Bang, what we call the observable universe. But with gravitational waves, we're no longer just seeing the universe. Now we can hear it. Gravitational waves were nearly impossible to detect because gravity is so incredibly weak. But that same weakness allows gravitational waves from the distant past to reach us without being disturbed. In theory, there could still be primordial gravitational waves from as early as 10 to the power of minus 32 seconds after the Big Bang. Now, for the first time, we have a way to listen to what happened in the universe before anything could be seen. 100 years ago, Einstein predicted that space-time would tremble, and now, 100 years later, our hearts tremble with it.